All right. Yeah, let's start. So last time we were studying about this echelon form, which basically represents formally the definitions and specification of this staircase kind of a shape, right? And then, yeah, we introduced this leading entry, which is like the first non-zero entry at each row. And then we discussed about these three conditions. And then we stopped at this second one, and yeah, it's written in a little bit tricky manner. And let me try to clarify a little bit more. So we can think about leading entry of each row, right? And then let's suppose this row is like the third row, okay, which is the third horizontal vector. And then we think of the position of these leading entry in terms of the column positions, okay? So let's imagine this kind of a matrix, and then we consider the second row, and then the leading entry is 3, and then this 3, I mean the position of this 3 is in the third column, right? Okay, then let's just use the row index as 2 because it was a second row, and then let's think about this position and represent it as this third column, which is in the form of this 2, 3. Okay, and so this row is a second row, and this leading entry is in the column, which is a third column. Okay, and then we consider the row above it, and so the possible row will be the first row, because we are considering the second row. And then so let's consider this case where the first row has the leading entry at the first position, which means we can represent that position as 1, 1. How about this case then? Still 0 and then minus 1. And then what should this number pair be? It's a 1, 2, right? So yeah, back to this sentence, we consider the row above it, which is a first row or even the other above row. But we consider the leading entry of the first row, and then it's in the position of second column. Okay, and then this column index should be, I mean, yeah, this column index or this column index should be to the right of the leading entry of this guy, which means this third position should be on the right hand side, of the leading entry, which is in the second column, okay, in case that leading entry was from the above row. And so it simply says, when just listing up the position of this leading entry as 1, 3 and 2, 2 and 4, 1, for example. In this case, all these three are leading entry. And then, does it satisfy this second condition or not? Is it or not? Does it satisfy? Or not satisfy? Yeah, it is not satisfying, right? So if we imagine the shape of this, so 1 comma 3, so we have to see 2 zeros before the first non-zero entry in the first row, and then in the second row we should see 0 and then the first non-zero entry here, right? So clearly from the shape, so we start from our staircase and then we go one step up or down, and then yeah, in order to cover this non-zero we have to go left, right? So it clearly violates our staircase shape. Okay, so staircase should always go to right or either down. Okay, so that's the meaning of the second item. Okay, and then again the and the third column, I mean the third item is about the following. So once we find any kind of a leading entry for this one or this one, and then you look down and then you have to see all zeros, okay, below that leading entry. And also for this case we also have to satisfy these. Okay. So that means if you like hit the wall, okay, so that is the meaning of the first non-zero entry, and then it should just yeah, we just have to go one step down, but not 2 or more step down, okay, because the height of wall is too high. So once you satisfy these 3 conditions, what was the first one? The first one was all 0 columns, all 0 rows should, yeah, we put all 0 rows to the bottom of the matrix. Okay, so that's another simple condition that we have to satisfy to make this kind of staircase. Okay, so that is the definition and yeah, like formal and mathematical definition about the echelon form. And then now we'll learn about this reduced echelon form. So in the case of reduced echelon form, there are 2 more conditions that we have to satisfy in addition to echelon form. So we now know the staircase is corresponding to the echelon form, but we have to satisfy 2 more conditions, and they are quite simple. So the first additional condition is that, so once you find these leading entries, so leading entries are quite important because that's kind of the actual walls that we observe when following this staircase. But that wall should have always the value of 1. Okay, so so in this case, yeah, so these 2 guys are our leading entry in this staircase shape, but clearly these are neither 1, right? So they are not 1, right? So how can we make them so that they can satisfy this condition? How can we make each of these values as 1? It's quite simple. So we have 3 possible operations that we can satisfy this. And so the easiest one will be just the scaling a particular row. So simply, once we see the leading entry which is not 1, and then you just simply multiply this row by -1. Okay, so you can easily scaling up or down this row, and that is actually corresponding to like x plus 2y equals 3, and then we can freely multiply this and then change it to maybe -2x minus 4y equals -6, right? So that doesn't change or affect the value of our solution in the linear system. Okay, so this fourth condition is simple, and then the fifth condition is a little bit more interesting, but not that difficult. Okay, in the echelon form, yeah, let's consider this guy. okay, the leading entry in the second row, okay, and then we know that the echelon form should satisfy, or should satisfy this condition of observing all zeros below that leading entry. So we look down, and then all elements should be 0, right? But in the case of reduced echelon form, we look also up in the direction. And so if we look in the upper direction, we also see this value. So we didn't care about what this value is, but we actually now care about this value, and then see if this value is also 0 or not. So if when looking in the upper direction, if we see all zeros, which means if I'm a leading entry, then I look down or I look up, and then I only see zeros, no other non-zero entries. In that case, we call that matrix as reduced echelon form. So this means we further reduced non-zero entries in the upper part of the leading entry. I mean, each of these are leading entries. Okay, and that is so when thinking about this original set of equation forms, so you guys know this matrix kind of things is always converted into a set of equations, right? And in these equations, okay, so this was the very first example that we studied in the last few lectures, and these are our staircase shape. And then we can easily make a leading entry as 1, and then we look in the upper direction, and then we create zeros here, and then it was corresponding to. So from the last equation, it was telling the exact value of an x3, and then we can just plug this value into here and here, right? So that was corresponding to making those two values as 0, right? So that is like, so once we created a staircase shape, and then the last equation will give you exact value for a single variable, right? Just like this. And then we just plug this value into the above direction, which involves more and more variables, right? So that way, we just create these as zeros, and at the end, once we do it, so we make these two values as 0, and then we go back to the staircase, okay? And then we now move on to the next leading entry, which was in the above column, and then we look in the upper direction, and then create this guy as 0, and this was a resulting form, which is really nice form, where each equation will involve only one variable. Okay, so that way we clearly solve this equation. I mean, we obtain the solution as this. So intuitively, we create this. This is the process of creating this reduced echelon form. So we first scan to the right and down to create the echelon form or staircase shape, and then starting from the leading entry at the bottom, we go back to the staircase while looking in the above direction, and then creating zeros in the upper part. And this kind of a scanning to the bottom right, and then scanning back to the upper left, that is exactly the same as solving this linear system. Okay, so we now learned about two different forms, echelon form and the reduced echelon form. Okay, and then there is a little bit interesting properties. So suppose I give you one set of equation, and then you can easily convert that into a matrix form, and then you try to create it into a staircase shape or echelon form. But those two students are solving on their own, and then their echelon form, starting from the same set of equations, I mean, their echelon forms might be different. So the echelon form can be different, but once each of these guys are also taking care of the upper entry from this leading entry, so that we create reduced echelon form. Okay, even if they have a different echelon form, but if they create, they change it further to the reduced echelon form, the reduced echelon form will always be the same. I mean, if they started from the same set of linear equation. Okay. Okay. I will not prove this. It's a little bit tricky to prove. Let's just understand that manner. And then in the case of, the fact that they can have a different echelon form is really easy. So in the case of this echelon form, this is clearly an echelon form, but how about multiplying this guy by 2 or half and so on? So that, in the case of multiplying by 2, it will be 2 minus 8, 8. In that case, does it satisfy the echelon form? It is, right? Echelon form doesn't need to have exact ones in the case of leading entry. The leading entry, the value can be anything, okay? As long as it's non-zero. So that way, the echelon form can be trivially multiple different versions. Okay. Okay, so again, reduced echelon form is unique given a particular matrix A, but the echelon form is not unique, but the echelon form will always exist. So one thing that that I mentioned. Another thing that you have to keep in mind is that, so is it possible that you cannot change one matrix into echelon form? I mean, for some matrix, I mean, it can never be converted into echelon form. Is it possible or not? I mean, is there any case like that? The answer is no. So given any matrix, you can always change that or convert it into echelon form, and then also reduce echelon form as well. So whether echelon form exists, okay, the answer is always yes. Okay, and then let's learn about the new term based on what we just learned. So this pivot position is has a quite important meaning. So pivot means, what was the pivot? Did I? Pivot is the leading entry, but this leading entry should be from your echelon form. So let's think about this matrix. What is the leading entry in the first row? This guy. And what about that? What about the second row? This is still a leading entry, and this is the leading entry. I mean, they are still called the leading entry, but this is not satisfying the echelon form. But still, they can be called a leading entry. But if we create this matrix into echelon form, for example, um, 0, 2, 0. So this has the staircase shape, okay? In this case, the leading entry is this guy and this guy and this guy. But those leading entries in the echelon form is actually called pivot, okay? So if your matrix is an echelon form, the leading entry is has a special name of pivot, and the position of this pivot will have a really important meaning. And the position of this pivot can be described as, they can be represented as this 1, 1, in this case, and 2, 2, and this guy will be 3, 3, right? So, so we can think about the positions of this pivot in terms of row position and the column position. Okay. So, so that was our pivot position, and then, more importantly, the columns of those pivots, the position in terms of columns will be also, will be more meaningful. That is kind of a meaningful part. Yeah, so I will tell you more about this. Okay, so here is one example, but this is almost the same as what we did in the previous lecture. So let's try to make this matrix as a staircase shape, but we see 0 here, so we should start like the staircase as this, but already we see -1 in the left side, and so we have to, it will violate the staircase shape, so we cannot make this -1 into 0 by using this 0, and so we can simply switch between them. So if we see 0, but if we see non-zeros below, and then we just simply switch and put this row to somewhere in the bottom. So let's suppose we change this guy with the fourth column. We can change the first row, the first with the fourth row, but we can also change the first row with the second or the third, because they have non-zero entries in the first position as well. But let's just pick up the fourth row, and then we just switched it, and then we have non-zero here, right? And so let's create the first wall here, and then make all these as 0, and then you know how to do it. We just multiply the first row by -1, and then add it to the second row, right? That way we can create this guy as 0. We can also do the same thing on this, right? Then we create all zeros, right? So we are kind of one step closer to echelon form, because for this leading entry, the elements in the below will all be 0. And then we move on, okay, to the second one, and then similarly we create these as 0, right? Yep. And we introduce these zeros, and then and suddenly, as we create these as 0, the staircase was reaching the far end to the right, because we happen to make them all 0. Okay, but in this case, so we reach it at the end, but we see non-zero in the below row, so we have to go to left, right? So that also violates our condition. So we can simply switch between the third and the fourth row. Okay, and then this is the result after switching between the third and the fourth row, and then our staircase has been completed. Okay, so far this is a leading entry, and then also this is an echelon form. So this is a echelon form, and then the leading entry of the echelon form is called a pivot. And then what is the pivot position? It's 1, 1. What about this? 2, 2. What about this? 3, 4, because it's in the fourth column. Okay, and then I mentioned that more important part is the position in terms of their column index. Okay, and I will explain why it is important in shortly. And then now we obtained echelon form, but we now it's time for making it further to reduced echelon form. So we start from here, and then we look in the above, and then create all of them as 0, and so on, right? Oops, yeah, from this one, yeah, from here we create these as 0. Okay, so this is another example. So in this case, we created this kind of staircase shape, and then in this example, for those pivots, we look in the above and create them as 0, right? So we created 2 zeros, and then go back to this leading entry or pivot, but here in this case we see 2, not 1. So we first scale it by half so that we create it as 1, and then for this we look in the above, and then we create it as 0. And then we move on to the first one, and so we scale it by 1/3 so that we create it as 1. So we still satisfy the echelon form, and then for each of the leading entry in this echelon form, we see all zeros in the above. But for this, there is no entries in the above, so we don't need to do anything for the first one. And so this is our reduced echelon form. Okay, so there is another term of a forward phase and a backward phase. So forward phase is a process of creating echelon form by just going down and to the right, and then we go back, right, to the left and the up. That is called a backward phase. Okay, so let's think about this matrix, and then see if this is first of all echelon form and also reduced echelon form. So this is our staircase, and then we look at this leading entry, and they are all 1. And then for each of these leading entry, we look in the above and in the bottom part, and then they are all zeros. And then this guy is a reduced echelon form, right? And if you remember, this matrix, when solving this linear system, creating this matrix as a reduced echelon form is actually the same as solving this linear system. So this one will give you x3 as 3, x2 as 16, x1 as 29, right? Because each equation is just like this values, right? But what if we have this kind of reduced echelon form? So in this case, let's convert it as just the equation. So it will be 0 equals 0. And then in this case, what should that be? x2 plus, right? Then x1. Right? So as it is, it doesn't give a exact value for x1, 2, and 3, right? It's still giving some equation, right? But this is actually your solution, okay? So in this case, is actually corresponding to the case where we have infinitely many solutions. So once you created a reduced echelon form, and that's it. I mean, there is no further, or I mean, nothing else that you can do, and you have to stop there, and then from this equations, you have to just express or give an answer for your x1 to x3. Okay, and how we can give the solution? It is like this: x1 is 5x3 plus 1, and then x2 equals 4 minus x3. Okay, so this is your solution. But this x3, yeah, what about this x3? So we have no clues. So in this case, x3 can be any value. So x3 can be 0 or 1 and minus 1 and so on. Any, yeah, basically any values. And then depending on x3 value, x1 and 2 will be decided. So if x3 was 1, and then x2 will be 3, and then x1 will be 6. So 6, 3, 1 is one of your solution. And then and then it was 0, and then it's simply 4 and 5, right? You just simply plug x3 value into the previous equations. So this is another solution. And so in this form, the solution will have, the number of solutions will be infinitely many. Okay, so that is corresponding to one of the 3 possible cases. So what was the 3 cases? So only one solution, or infinitely many solution, or no solution at all. So this is corresponding to the case where we have infinitely many solutions. Okay, and then so this is your solution, and in this case, this x3 value is called free variable because they can be any value. Okay, so you can freely assign any values to this variable. And then there are 2 other variables, x1 and x2, and these are decided depending on your free variable. Okay, so you have a free variable, you can freely choose any value from, and then there are other variables that are kind of decided depending on those free variables. And then these variables are called a basic variable. So basic variable and free variable, those 2 are the important classification of your variables into 2 different types. Okay. And then this free variable and basic variable is actually corresponding to, I mean, they are related to the position of the pivot. So let's look back at this reduced echelon form. And then I previously mentioned that the position of those columns for these pivots is important, right? And so the first column was corresponding to the first the variable x1, and then this is x2 and x3. Okay, and so here, but what about the last one? What is corresponding to? So these are corresponding to the constant, right? x1 plus 2x2 equals 3, right? So this 3 will be put in the last column, right? So this is corresponding to something like b, or some constant that we extracted out from each of these equations. Okay. So here, the position of the pivots is located in here and here, and let's think about their column position, and this is corresponding to x1 and x2. Okay, what about x3? So we still have another variable, but in that variable or in that column we don't see any pivots, which means in any rows doesn't have the pivot in the position of x3. Okay, so let's relate this characteristic with this free and basic variable. So in this case, this column which doesn't have any pivot, in that column, that variable is will become your free variable, and those variable which has the pivot positions in some rows. Okay, in that case, those variables are basic variable. So again, free variables are determined, basically freely by setting any values, and then those basic variables are kind of decided accordingly. I mean, depending on those free variables' value. Okay, and then in this reduced echelon form, let me ask one thing. So here, in this case, is it pivot or not? This is not pivot because in this corresponding row, we already see the pivot in the left side, right? And then, so for this case, please note that for this non-pivot values, it doesn't need to satisfy all zeros in the below and the above part. So that's why, even though we see 0, but in the above case, above values, these are not zeros. Okay, so still it is reduced echelon form. Okay, we only look at the pivot. Okay. Okay, and then obtaining these kind of answers for our solution. This is actually solving the linear system, and also this form is called parametric description of your solution sets. Okay. So parametric description means you have some parameter that you can tune or change freely for these free variables, of course, and then depending on these free variables, the solution is determined. But you change the free variable to another value, and then you change the solution accordingly, right? So that will be included in our solution set. And in this case, since you have a free variable, and so in this case, the solution, the number of solution is infinitely many, right? But if you don't see any free variables, and then it will be corresponding to like unique solution. Okay. So so once you look at the position of these pivots after you create reduced echelon form or even echelon form, you can immediately answer the number of solution from just the shape or the position of this pivots. So let's think about just the one possible case. So in this case, so we have 4 columns, and then pivot was corresponding to x1 and x2, but not x3 or not B part. Okay, but the pivot can be sometimes belonging to x3 and also B as well. Okay, and then yeah, we will think about a few different cases in terms of these positions of the pivots. Okay, that will actually tell you the number of solutions. Then let's think about the special case like this. So in this case, let me just clear that. In this case, okay. So suppose this was your reduced echelon form. And in this case, the pivot position was x1, x2, and also b part, right? And so this one is having the pivot in the b part or the column belonging to b. And then let's think about its equation form. It will be 0 equals minus 1, right? So that clearly means you have one equation that never be true. That's never be true, right? So in this case, the solution doesn't exist at all. Okay. And then, so the other case will be no pivots in the column of B, just like this. Okay. So in this case, we have this kind of a shape, and in this case, the solution at least exists, yeah, whether it's a unique solution or infinitely many solution, because we don't see any pivots in the column of B. Okay, but whether it's a unique or infinitely many solution is determined whether by determined by whether you have free variable or not. Okay. So from this equation, x3 can be any value because you have a free variable as x3. So yeah, it will create infinitely many solutions. But what about the case where you have no free variable? So in that case, let's think about this case. So this value was 1 and this value was 3. And then the staircase shape is something like this. So you have pivots in x1, x2, and x3, right? So if you look at this vertical columns, x1, 2, and x3 will be all having a pivots, right? And it means x1, x2, and x3 are all basic variable. And what about free variable? Are there any free variables? No, right? Because all of our variables will have one pivot, which means no variable. Each variable will have a pivot, right? So there is no variable that doesn't have a pivot. So in this case, there is no free variable. And then let's think about the solution of this. In the case of the third one, is x1 equals 3, x2 plus x3 equals 4, but we can plug that in, right? And then x1 equals 1 plus 5x3, so x1 can be plugged into x3, right? So in this case, there is no free variable, so in that case, you will have a unique solution. Okay, so this theorem is just what we learned before. And so once you see, yeah, so this is about the existence of the solution. I mean, those three different cases that we considered are formally described by these theorems. And let's follow this. So we want to decide whether the solution exists, and then if the solution exists, is it just only one, or it can be many solutions. And so these are the rules that you have to follow. So once you see the rows like this in your echelon form or reduced echelon form, then it will be corresponding to having no solution, because in your matrix as an echelon form, somewhere in the middle, you found that all zeros except for the last value as non-zero, like this. Okay, so this is an echelon form. So the leading entry in each column will be your pivot. And then this pivot is corresponding to the column of B, right? And then this equation will correspond to 0 equals 3. So that will give you no solution, right? So you first check whether this column is found or not after you create the echelon form. Okay, and then yeah, let me ask another thing. So if this was an echelon form, suppose you have 2 more columns in the bottom part of this column, this row. So in this case, we have 2 more rows below that row. What is the possible rows for these 2? What should these rows be? It should be all 0. Does it make sense? So if it is an echelon form, this satisfies the staircase shape, and then this one is the first wall that you hit at that row, right? And then you have to go to the right or down, and then if we see non-zero, for example, like 1 here, and then we have to go to the left, right? So it doesn't satisfy the echelon form, right? So you can either go to right or you just go up. But in that case, you cannot go down as well, because we have to see 0, because we cannot step up 2 levels higher. So 2 levels higher, it's not possible, right? So this one, it should be pivot, and then the entry below it should all be 0. So that means all these rows below this row should be 0 rows. Okay, so once you check whether this type of row exists or not in your echelon form, and then we can determine whether the solution exists or not. And then suppose you didn't find any kind of row like this, okay, which means you don't see any pivots in the column of B. In that case, it means you at least have one solution, but you still have to determine whether the solution is just one or infinitely many. And that is determined by whether you have free variable or not. Okay, so if you have a free variable, then the solution will be written in this kind of a form, right? Not as a particular value, but in the form of those free variables. Okay, so in that case, the solution is infinitely many. But in the other case, where you don't have any free variable, and then you now have one unique solution. Yeah, that's it for the second chapter. I mean, the chapter 1.2. And any questions? 쓰는 게. So the so the first homework was posted, right? And then it's due by the next Monday, by the end of next Monday. And the first homework is the goal of the first homework is to train yourself about these kind of process. So you just studied or looked at maybe two or three examples during this class, but you may not have a kind of clear idea about what's going on. But once you solve it and then get a hands-on, I mean, you actually do this kind of process of creating echelon and reduced echelon form, you will really have a clear idea about what this lecture is about. So that's why I gave you the homework a little bit early. And the question was, do we have to write what kind of a row reduction or row operation that we did? For example, I scaled the second row by 1/2. Yeah, just like this, and then like this. Okay, so yeah, please specify or write clearly what your operation was. Okay. Any questions? So if you didn't understand, it's time for you to ask freely. What you didn't understand. So feel free to ask me any questions.
Is this an echelon from matrix 1100 1010 0110?
Yeah, the question is whether this is an echelon form or not. Yes. Or no. Again, yes. So the process is simple. I mean, I think you guys have a good understanding. So we look at each row and then find the leading entry. So in the first row, the leading entry is this guy, and then the second row, the leading entry is this guy and this guy. Okay, and then you check each leading entry and its elements below it and see if they are all 0. But in this case, you see non-zero values, right? So that doesn't, that is not satisfying the echelon form, right? And also, in terms of kind of staircase, so you hit the first wall, and then you can go only one step higher, but it's already like the wall of like too high, right? So once you hit the wall, and then you have to at least go to right. Okay. Any other questions? And then let's think about some other case because the student asked a particular case. So based on the rules that we learned here, so we first check whether this kind of row is found or not. Okay, and then once we checked there is no rows like that. Okay, and then at least we can guarantee that the solution exists, whether it's just one or infinitely many solutions, right? And then after checking that, you check next whether you have a free variable or not. So if you have a free variable, and then you will have an infinitely many solution. But if you don't have any free variable, and all the variable, which means all the variables are basic variable. In that case, you have a unique solution, right? So there is no column, no rows like that, and also every column for your variable will have the pivots. Okay, so that means you have unique solution. And then let me ask this case. I didn't tell you what the equation is, but I'm gonna give you the shape in terms of this matrix. So you have the matrix which has 3 rows and 5 columns. And in that case, is it possible to have a unique solution?
No. I think no.
Yes, it is possible. It is not possible. Okay, so yeah, let's imagine the original case. I mean, what was the original case? So we have 3 equations, and what about the number of variables? 4, right? The last one is corresponding to b, and the first 4 is corresponding to 4 variables of an x1, x2, x3, and x4, right? And so in general, I mean, what does our intuition say? We have 3 equations and 4 variables. Is it possible that we have a unique solution? No, right? So in the simpler case, we have 2 variables, but we only have 1 equation. In that case, yeah, it can be infinitely many solutions, right? So in this case, yeah, it's the same thing. So it's not possible that we have unique solution, right? So let's try to understand that by relating it with the pivot position or the columns of pivots. So unique solution means we have to have all the basic variables, not free variables. So this x1, x2, x3, and x4, and b, this guy should have a pivot. And in the case of a reduced echelon form, yeah, let's put 1 here. And then what about this one? It should have a pivot, but it cannot be here, because if it is belonging to the first row, it is no longer a pivot, or it's no longer a leading entry, because we already find the leading entry here. So we have to at least put this leading entry or pivot in the second one. Okay, so far so good. And then the third variable, let's put the pivot here. And then what about x4? So there is no rows remaining where we can put the pivot in the first variable, right? So that way, once we think about the staircase shape, and then thinking about the possible positions of those pivots in the column positions, and then yeah, it clearly says, yeah, it's not possible that we have, it's not possible to make each of the variables as a free variable, basic variable, right? But in this case, it is possible that free variables can be like the first one, or the second one, or the third one. So in this case, what are the basic variables? So we created staircases like this, and then we see the pivots here, and then it's corresponding to x1, 2, and 4. So those 3 are our basic variable, and then the third one, x3, is a free variable. Okay, and then yeah, if you obtain this kind of matrix in your exam or homework, and then you learned about the parametric vector form, and so your correct answer should be x1, x2, x4 is something, right? And then this x3 is somehow involved in this expression, right? Because x3 will be our free variable, right? Okay, and then let's think about some other case where we now have, so this is like a very short and fat matrix, and then let's think about like a skinny and tall matrix. Okay, so we have 5 by 3 matrices, and in this case, the question is the same. Is it possible to have a unique solution? Or, let me ask this question first. Is it possible to have at least one solution? So we have 5 equations and then 2 variables. Is it possible that we can have a solution?
Only in some cases.
Only in some cases, right? But what about, when we have a solution, how should the staircase look like? Something like this should be our staircase. Okay, so far so good. And then let's imagine we have 1 here, and then the staircase will be like this. In this case, it is corresponding to having the row of all zeros except for the last non-zero one. And then this guy is 0 equals 0 equals 1. So it clearly says we have no solutions, right? But can we avoid this situation? I think yes, because you see all 0. And then the staircase is just ending here. And then the remaining 3 rows will be all 0 rows, so that we can satisfy these staircase shape. So in this case, we do not see any zeros, any pivots in the last column, right? So we are happy because we can now guarantee that we have at least one solution. Okay, and then let's see. So in this case, how many solutions do we have? Infinite solution? Why? Why do you think so? I mean, whether we have an infinite solution or single, only one solution was depending on whether we have free variable or not, right? So let's think about what variables are free or basic ones. So this is x1 and x2, and this is b, right? Okay, in this case, let's figure out where the pivot is. And then pivot is here and here, right? And then it's corresponding to x1 and x2. And so we have 2 variables which are all basic variables because they all have a pivot in the corresponding column. So in that case, we have a unique solution. Okay, and then let me ask another question. So is it also possible that we have infinitely many solutions? So in other words, if we imagine the original equations, we have 5 different equations, but we only have 2 variables. But still, is it possible to have an infinitely many solution? Yes. Yeah, the answer is yes. So in this case, how should the staircase be? So in order to have an infinitely many solution, we have to have a free variable. That free variable shouldn't have a pivot. And then the possible staircase that I can imagine is just this. Okay, it's a really boring staircase, but it's still a staircase, right? So it means we see one, some non-zero values or zero value. Yeah, we do not care about those values. And then the fact that the staircase has ended, right? We see all zeros, right? Like this. Okay. So in this case, the pivot is only existing in the first one, and so it is corresponding to x1, right? But x2, in that column, we don't see any pivots. In that case, yeah, we have a free variable that works as a kind of a parameter in the expression of the other basic variable. Okay? In that case, we can say that this one has an infinitely many solution. And then, yeah, let me give you just a special case, which is really trivial and easy to understand. I mean, corresponding to this case. So we have like a 5 different equations, and then I'm gonna give you the 5 different equations as this: x1 minus 2x2 equals 3. This was the first equation, and 2x1 minus 4x2 equals 6. 3x1 minus 6x2 equals 9, and so on, right? So in these cases, even though we have like 3 or even more equations, they are all just one single equation. They are all the same with each other, right? So in that case, you still have an infinitely many solution because we actually have only one meaningful equations, and then having still 2 variables. And once you have these types of equations, and then if you create a staircase shape, and then it will give you exactly like this kind of a staircase shape. Okay. So this process of creating the staircase shape is actually the process of revealing which equations are some meaningful equation or not meaningful equation. Okay. So not meaningful equation is actually removed after this process. Okay, and then let's think also about the special case where we have a unique solution. So unique solution, yeah, in terms of its reduced echelon form, yeah, since we have a unique solution, we have to make the pivot in each column for each of our variable, except for the last column, of course, right? So let's start with the one here. Yeah, I'm not gonna specify the matrix size first in this case. So we created this staircase shape, right? So we should have all zeros, right? All zeros below it, and then at this point, what should our choice be? What is our choice? I mean, what is the possible choice? We can go to right or up. But if we go to right, then it means we still see 0. We didn't hit the wall yet, right? And then let's suppose we hit the wall here. And then, yeah, so the staircase is like this, right? In that case, x2 variable is already what? It is already becoming free variable. So there is no other chance. So once you pass the previous variable, and then you have no other, you have no way to go back and create a pivot in the corresponding variable, because you can only go to right or down. Right? Okay, so in this case, x2 is becoming your free variable, which means there is no it's not possible anymore to have a unique solution, right? So unique solution case is actually just a staircase of just like this. So one step down and one step to the right and down, right, and so on. And since the pivot value should be all ones in the reduced echelon form, and then we can have this kind of staircase shape up to the total number of variables. So if we see 100 variables, and then if we have to have a unique solution, and then the staircase shape should be all like this kind of exact diagonal case, all the way until we hit the 100 and by 100. Okay. Okay, and then what about the next cases? So this was our last variable, and then how many columns can we have? I mean, how many more columns can we have on the right side?
Only one.
Just one. Can we have two? It doesn't make sense because we already assumed that x100 is our last variable, right? So we can only have one column, right? Okay, so we only have one column, but what about the number of rows? So in terms of the extending the column, we can only extend one more column. Okay, what about extending the rows?
Infinitely. Not more than 100.
Yeah, so this one was like 100th row, right? And then, so at this point, we can just, only go to right? But what about this part? As long as this part becoming all zeros, and then it doesn't affect our solution, right? So that is kind of a meaningless equation, just like those guys. Okay, so we can have basically unlimited more equations. Unlimited number of equations, but those equations should be meaningless equations. Okay. But can we have less than 100 rows? So we can now understand that we can have unlimited number of more rows, which are just meaningless equations for rows. But is it possible to have less number of rows than 100? Can we have like 99 rows given we have 100 variables? It is not possible, right? Because we have to exactly create the staircase as an exact diagonal shape, right? So at least we have to have 100 equations in order to have unique solution, right? So that is obvious once you just think about the number of equations and the number of variables. Okay, then see. Okay, and then I'm gonna give you another homework, which is to understand this slide, this exact page. Okay, this is really easy, but I want you to think a little bit more about it. And so the parametric solution, parametric form, where we put all the free variables on the right hand side. Okay, you can actually change your free variables using some other variables. So you can have some other forms of the solutions, but we do not use this form. Okay, it's our kind of promise. So there are many possible ways of describing your solution, but yeah, we kind of promised that we only use the basic variables on the left hand side and the free variables on the right hand side. Okay, so this slide is about that. Okay, but it's should be easy to understand, and yeah, that's it for today. And please make sure to submit the homework as a kind of paper one, and also the electronic one by submitting it online to the Blackboard or KU LMS. Okay. Okay. Thank you very much, guys.
Should I have class so that I can go on with the children? I did understand it.
Sure.
We are reducing the interim form by how? Because
Okay. So
this one.
yeah. So we see 0 here, right?
So we flip it.
Yeah,
to
we
the,
flip it. Then
change.
yeah, this is the resulting one, and then we see the first non-zero here,
Yeah, big.
and then we have to make the entry below it as all 0.
Yes. Okay.
And how can we create 0 here? We just multiply
By minus.
-1 and then add that to the second row. Then we create this one as 0. Okay, and then we are now happy for this one.
Yes.
And then we move on to the second one. And then we look at the bottom part, and then we create this 3 as also 0. How? We just multiply it by 2/3, -2/3, and then add it to the third one. Okay.
That's it.
Yeah, that's it. For the fourth phase,
Step 4.
yeah, and then this was fourth phase. And then we now have a pivot here, here, and here. And then in order to create a further, as a reduced echelon form, we look in the above. And then we create 2 and 6 as 0. And how? We simply add -2 times this guy into the second one.
Yeah.
That way we create 0 here, and -6, add it, then we create 0 here.
So why do we create 0?
Huh?
For what?
It's like removing the variables, as many variables as possible in the above equation. So in general, this kind of staircase shape means you have more variables in the upper equation. Is it right? But we want to remove the variables as many variables as possible in the above equation.
Okay.
So that's kind of an intuitive kind of process. Yeah, the reason for it.
Okay, thank you. Can I have that?
Oh, sure.
Yeah, thank you.
I proved this equation all 0. x1, x2, x3, x4, x5, all 0. But if we have 5 columns and the 4 equations of 5 equations, 6 columns, and the last column is all 0 column, and all the equations are meaningful, then the solution is only 0, 0, 0, 0, 0.
So we have 5 variable, right? Then we have 5 equations.
Yeah, and the last column is
All 0.
only all 0.
Okay. Okay.
And the solution
Yeah.
must be only 0. Only one thing, only 0.
Only unique. You have a unique solution.
Yes, all 0. x1 0,
Okay.
x2 0,
Yeah.
x3 0.
Okay. So that is a unique. Is that unique solution, right?
Right.
Yes. Yeah.
So in other cases, such as 4 equations, 4 variables, the 5th column is all 0. Is the same?
Yeah, but
Same kind.
so suppose this guy was pivot, okay? But you don't need to have exactly 0 here. So you can have non-zero because this is not a leading entry or pivot, because you find the leading entry here, right?
Yeah.
And then this can be any value,
I
whether it's
know.
a 0 or not.
I know, but I'm talking about some special cases. The last
Yeah,
column all
right.
0.
Yeah, in that case, whether the solution is 0 is not related. I mean, it doesn't matter. It's not related to the number of the solutions. Okay.
Oh.
So the actual value of the solution is 0 is not directly related to the number of solutions.
Oh.
Right.
Right.
Yeah.
교수님 마지막에 그 과제 28번
네.
페이지 이렇게 그냥 이해를 하라고 하는 거.
아, 예. 공부